right. Before going back to talk about water and so on, let me remind you, the second midterm in this class is on Monday, the 28th. As always, it'll be 30 multiple choice questions, same as I've done for the past 5 or so years. I totally encourage you to take the old exams. You'll learn a number of things from them. You'll be more comfortable with my kind of questions, for better or worse. I ask them sort of the same way. You'll see some questions you actually will see on this exam, because that's what happens. I reinvent them or I steal them. You'll see, in particular, what things you don't understand well, and that'll give you a guide to go back and look at what is it that, look back through the materials, your notes, the book, maybe the old videos, to try to fill in things that you don't understand well. So don't just leave the exam, take the exam, don't look at the answers, take the exam, and then go back and find out what it is that you didn't understand in the questions. So don't just walk away from the exam after getting your whatever score you get. For those of you who stick around too long, turning right answers into wrong answers, learn when to stop. And part of that might be to finish the exam, record your choices, and then go back and suffer over some of the questions longer and see whether you turn right answers into wrong answers or vice versa. Any questions about the exam things? Oh, it will cover material primarily from after the first midterm. That is sort of carousels and beyond, through the fluids and all that. But physics is inherently cumulative, so some of the stuff will just show up anyway because it's still relevant. And I will also go back and ask some questions from the first, essentially third of the class, just because I can, okay? Finally, office hours. I'm going to move my next Monday's office hours from the afternoon, when they're normally held in Alderman Cafe, to the morning in Alderman Cafe. So if you want last minute questions, I'll be there 9 to 11 in Alderman Cafe to answer any of your questions. Okay? All right. Before going back to sort of the complexities of water, that's what I feel like I'm in the middle of talking about, the stuff with garden watering, all the things that make water and fluids more complicated than just delivery. I'm going to roll back to the siphon. And why? Because it came up a couple days ago about television and Emmys and stuff. And okay, so I've done a lot of television, which has been fun, particularly not as my day job. It's a tough day job doing television. But so it's always been science television, so I'm always playing myself trying to explain science. And just observation, it's very hard to get real science on television, because the first priority of television executive producers, is to stop you from changing channels. And every moment of science on television is viewed as an opportunity for you to change channels. So it's tough. I've worked very hard to say as much as I can in as few words as possible and then disappear. All right? Back in 2007, I was a co-host of a Discovery television series called Some Assembly Required. And we went into factories, like 26 or 28 factories, and we made stuff. And I was the science guy to explain how and why this is happening. And we made everything from guitars to whiskey. And one of the things we made was toilets at Kohler in Wisconsin, not surprisingly. And I got to talk about how siphons work, among other things. And so here it is, okay? Something, is it there? Oh, yeah. So this guy has been molding toilets, and now it's a moment to go over to the science guy.
Drainage happening. You're like a chef making a 5-course meal here, except it's a toilet.
That's the main host, Brian.
Today we're making a jet-assisted toilet. That's Kohler's answer to creating more efficient toilets. In 1994, Congress passed a law that requires toilets to use less water, no more than 1.6 gallons.
The way this toilet does it
is by feeding most of the water from the tank through a jet where it comes on a very high flow rate, picks up the waste, and blows it through this curvy tube known as the siphon. Now, as the water goes up and over the siphon and down the far end, the weight of that falling water and waste creates a partial vacuum at the top of the siphon that sucks everything else out of the bowl. But when the job is done here, the bowl is empty and everything is in your plumbing.
So that's where that hole is being made, right here. That's the jet hole. That's the jet hole.
All right. This segment goes on to simulate, later on, simulate the flushing process with something real to go down. And what they use is meso paste in condoms. And they flush those down. So I'm not going to go there. All right. Back to business. And the business is the complexity of water flow, say in garden watering. I've talked a little about viscosity, the idea that actually the real fluids have the ability to push on themselves as they slide across each other. So layers of air, for example, air has a viscosity. It's not zero. It's got some of these viscous effects. As layers of air slide across each other, they rub against each other. So, for example, the air on this table, sitting on the surface of the table, is motionless. Why is it literally motionless, and how to deal with it? That's more a job for theoreticians. But you can treat it as motionless, and that's a pretty good description. And as I walk by here and I'm moving the air with me by pushing on it, I've got air here moving and air there not moving. There are effectively layers of air that are sliding across each other, and that has effects. I mean, in this case, they're small, because air doesn't have much viscosity. But if it were water, the effects would be bigger. And if this were honey, if we were immersed in honey and I moved along like this, the effects would be big. So anyway, that's the story of viscosity. I talked about it in the context of water going through a pipe or going through a hose to your garden. The water struggles to get through that pipe because of viscous effects. The water at the pipe surface is motionless, and the rest of the water has to deal with that. And it's tough. And if it were honey, it would really be tough. All right. Second issue of complexity that I started talking about last time is turbulence. And that is that water doesn't always flow smoothly where it goes from one place to the other in sort of an orderly fashion. Sometimes it breaks up into sort of individual portions that head on their own. And that happens when inertia begins to dominate the motion. When the pieces of water, the portions of water, because of their inertia associated with that, because of their momentum, they just keep doing what they want to do, and they separate from each other. They tear apart, and you end up with turbulence, which the hallmark of which is vortices, swirling stuff, and the tumbling of like white water. So if you've ever watched water in a stream or water out of your faucet where it just swirls around and turns white, that is turbulence. And viscosity favors laminar flow, inertia favors turbulence. And there is a number known as the Reynolds number, and it's a pure number, it has no units, that takes the ratio of inertial effects to viscous effects. And if that number is big, meaning inertial effects are bigger than viscous effects, you tend to get turbulence. If that number is small, meaning that viscous effects are big compared to turbulence effects, you tend to get laminar flow. The Reynolds number is very useful to engineers and stuff in trying to figure out how things will happen, and we'll use it a little bit in concept mostly. But there are various theories about the transition from laminar flow to turbulent flow at a certain Reynolds number, and it happens to be roughly 1,000 or 2,000, but nothing to remember. All right? Third complexity of water now, so I can bring up something new. And that is that when water or any fluid is moving around and accelerates, it accelerates, and gravity wasn't the cause of the acceleration, then the acceleration is caused by pressure differences. And those pressure differences sometimes arise because of the movement of the fluid. So there's an interplay between the flow and the pressure. We've already seen that that happens. You can convert kinetic energy into pressure potential energy and vice versa and so on. But some interesting or very interesting, important, surprising other things, effects occur. And to show you this, I'm going to actually show you. I don't normally put up graphs of stuff, but I'm going to do that right now. I did it. Okay, good. And the chit chat up there you can look at or not. But what I want you to look at mostly is this. Come on, is this curve over here? Thousands of laser pointers. Some of them work, some of them don't. Okay, we'll go with blue, woo, because it's working today. All right, what this drawing is showing is a view looking down on a hose lying on the ground. And we sliced off the top of the hose so that you can, half the hose off so you can sort of look inside it. And we see the hose lying on the ground, water entering from this lower part and going around a turn and coming out the right-hand side. So the water in this hose is turning, and it's moving while it's turning, so it's accelerating. It's changing its velocity. And weird things happen to the water, particularly the water's pressure in this context. I've drawn lines, the lines of flow along the water in this hose. They've got a name in the world of fluid dynamics. They're called streamlines. And it's a word that hopefully you've read about in the book or the lecture videos. They're in concept. They are the paths that drops of water take in laminar flow. In turbulent flow, you don't get streamlines because it's a big mess. In laminar flow, you get these streamlines, meaning that a drop of water that arrives at this location in the hose follows that line the whole way through and emerges at the other one. And it's like a parade. They all follow the same path. Every drop that enters at this point follows the same path. The streamlines here are different. They have different histories, meaning that a drop that travels this streamline never travels the other streamline. They're just separate characters in the story. And that matters in some contexts where the water along one streamline has more energy per drop than water along another streamline. And therefore, you don't want to compare them. You really want to compare water that travels the same streamline. And you can, if you watch water that travels the same streamline in steady state flow, that water, because every drop's the same, every drop has the same history ultimately, they all experience the same rises and falls in pressure potential energy or kinetic energy or gravitational. That's the simplest collection of water droplets to follow. All right, having talked this to death, the streamlines, look at the streamlines as they go. Notice that the streamlines, as they go up here and go around that curve, the streamlines change spacing. As they get to the curve, the streamlines that are out here on the outside of the curve, that's what I call the outside. This is the inside of the curve, outside. The curve is basically the water is traveling kind of in a circle, like a quarter turn around a carousel. If it kept the carousel going, it would go around in a circle, but it's going a part of a circle. And so it's accelerating toward a center, which is located somewhere around where my dot is. That's the center of the curve. This is the inside edge of the curve, and that's the outside edge. Is the language okay? Anyhow, the streamlines along this curved area are not evenly spaced anymore. They started evenly spaced. What happened? Well, up here, where the streamlines got farther apart on the outside, the water slowed down. It slowed down because it's basically going through a diffuser. It's basically spreading out and slowing down like cars coming out of the neck of a traffic work project on the road. They come out into full lanes and they can slow down. This is my bumper-to-bumper traffic analogy. On the inside of the turn, the streamlines get closer together. So they're kind of like going into a nozzle. They're necking down, and they have to speed up in order to flow through there in that thin, tightly spaced arrangement. So the speeds are changing. So I've got here on the outside marked low speed. The water in this hose on the outside of the turn has actually slowed down. It's real. If you were, put a little bug inside there, we notice, wow, the water's not going this fast. And on the inside of the turn, it's high speed. The water has actually sped up. Okay? It does mean that water that entered this hose all together in a line left to right, as it goes around, it slows down on the outside, speeds up on the inside. The inside water comes out of the hose first. If you wrote with a marker, you wrote color across that water as it went through, it would get all out of sync by the time it left. The water on the inside, the marked portion of water would emerge from the hose first. All right? The other thing that happens, and the thing that drives the whole turn, is there's a pressure imbalance inside this turn area. The water doesn't accelerate for nothing. It accelerates in response to a force. Something's got to push. And the push should be toward the center, because that's the direction of the acceleration. As you go around a carousel, you accelerate toward the center of the carousel. So the water is being pushed towards the inside of the curve. By what? By an imbalance in pressure between high pressure on the outside of the turn and low pressure on the inside of the turn. So there's it's a sheltered environment, that is, it's inside the hose. So air pressure outside, the atmospheric pressure, has no say in what the pressures are like inside this hose. And once you turn the water on and let it go around this curve, when everything settles, there's some transient stuff when you first turn the water on, which we'll just ignore. But once the water's flowing steadily, you got this weird arrangement where the pressure on the outside of the turn in the hose is high. It's the highest pressure in the story. And the pressure on the inside of the turn is low. It's the lowest pressure in the story. And it's sustained. If you drill a hole in this hose and look in there, that's high pressure water. If you drill a hose in here, it's low pressure water. Okay? I'll show you one more graph like this, drawing like this, and then I'll show you this in real life. Okay? So here's another one. This is the flow into a nozzle. And the water enters from the left. We're looking essentially down on a nozzle. Gravity's not part of this story. If it takes place in small environments, gravity just is irrelevant. So the water enters the nozzle. I told you about high speed. Oh, that's good enough. Okay. The water enters the nozzle, and it necks down as it goes through the nozzle. Well, for that to happen, it has to speed up. And we saw this when I was spraying water around. You send water into a nozzle, as it necks down, it converts pressure potential energy into kinetic energy. And sure enough, that happens. You can see the speeding up conceptually. I mean, the fluid dynamicists, or whatever they call themselves, would look at the streamlines and notice they neck together. And for them to bunch together, the fluid's got to be going like crazy through it. At the same time, the pressure drops because the energy doesn't come from nowhere. Some energy has to be turned into kinetic energy to make it go fast. Where did it come from? It came from the pressure potential energy of the water. So the water started at high pressure here. And in my drawings, I illustrate that with the color blue, or aqua. This is normal hose pressure water. But as the water goes farther into the nozzle and speeds up, its pressure goes down, as indicated by a shift in the color towards the red end of the spectrum. I make low pressure red and high pressure violet. It's the rainbow spectrum in my drawings. And so the water is speeding up and its pressure is dropping in a nozzle. I already talked about this more or less back with the water delivery, but here now you're seeing sort of why it happens. Which comes first? It's a chicken or egg problem. Which comes first, the speeding up or the pressure drop? They come together. They go hand in hand. When you start the nozzle, things are complicated, but once it hits steady state flow, that is, you no longer see this passage of time, it's like this. The pressure's dropping. So all the nozzles you've ever played with, many of which weren't called nozzles, the pressure starts high before the nozzle. As it goes through, the pressure drops, typically to atmospheric pressure, if that's where you're working. If you're spraying water out into the open air, the final pressure it has is the ambient one, the atmospheric pressure. So you start high and go low. back to atmospheric. If you have the opportunity to spray water or air into vacuum, the pressure, of course, can drop all the way to vacuum. All right? So wouldn't the pressure be higher before the nozzle as the water pushes more against itself as it slows down? There's some weird stuff that happens at the entrance to a nozzle. This is actually a calculation that generated this, but depending on how I make the nozzle, the water that's coming in here and starting to bend can actually build up high pressure, sort of as the water slams into that leading edge of the wall. So you can have high pressure here at these curves. It's not the water pushing on itself so much as it's the water encountering the surface and having to accelerate away from the surface. How do you get it to accelerate away from the surface? Build high pressure there. And so you can have high pressure showing up in these kind of parts of the nozzle. That is true. I should point out, applications. Why does this matter? Hose, yeah, Reed? How do you know something's high pressure? If you insert a little test tube, a little tube in there, for example, to go and measure what's the local pressure there. And if you put it at right angles to the direction the fluid is flowing, you'll get its local pressure. And just to see what pressure do you have, how hard do you have to basically push on the column of fluid in your little tube in order to keep the fluid from moving. If the pressure's high, you have to push back hard. And where I'm going somewhere with this, so I appreciate the question. It's, if you've watched airplanes, or you've looked at airplanes before, as you're boarding, you might see little things, gadgets projecting off the side front of the airplane. Little tubes that come off the side and stick out into the flowing airstream. I'll draw the gadget I'm talking about. So here's the body of the airplane, and sticking out it's sticking on a post. It's a tube that points like this into the onrushing air. So this is where the pilots are up in here and stuff. You see that thing there. It's called a Pitot Tube, and what it does is it compares the pressure of the flow at right angles with the pressure of the air hitting the front of that Pitot Tube. And I'll tell you, its purpose is to say how fast is the plane moving through the air. The measurement made to the side, the measurement made here, just tells you what's the local air pressure. That's what's the local air pressure the plane is flying through. This one is the air that goes into this tube slows down and comes to a stop. It converts all of its kinetic energy into pressure potential energy. So you get high pressure in here because the air is coming at you at 300 miles an hour. It turns that into pressure potential energy. If you're going 500, it turns it into more pressure potential energy. And by comparing that rise in pressure, the high pressure in this pipe, with the measurement of the ambient pressure, you can tell how fast the plane is going through the air. You okay with that idea? Next time you get on a plane, look, they're easy to see. They just stick out of the planes. So you can go into this pipe and sense the high pressure. You can go into the pipe here and sense the low pressure. I'll show you in a minute. We can actually notice it directly, even more directly. I will point out that when hoses burst, they often burst on the outside of turns. For this reason, the pressure's high there. It blows out the side. Sad but true, our plumbing, human plumbing, arteries and stuff, when they burst, which they do from time to time, they typically burst on the outsides of turns because that's the high pressure spot too. Right? So people, strokes and aneurysms and stuff, it's typically on the outside of the flow. Okay? Other questions? So let me play fun and games with this stuff. I guess I can leave that up there, I guess. First one. So what I've got here, where's air? Doing this with gas is not as good. All right, so now this is air, and if I turn it on, I'll get it to go right. Yeah. Okay, so it's a plate with air that can just roar out of the center of the plate. And by itself, it's just a loud, noisy thing, okay? If I bring a second plate up against that plate, you might think, well, of course it's going to blow the extra plate across the room. But a weird thing happens when the plates are very close together. What happens then is the air has to neck down to get through the narrow gap between the two plates. It goes out, of course, in all directions, but it's a very narrow neck. So it has to speed up like crazy because it's coming through essentially a pretty wide hose, and suddenly it has to go through this terribly narrow crack. And it's essentially going through a nozzle. It's a weird shaped nozzle with the same ideas there. And when it does that, it speeds up and its pressure drops. And it's in a protected environment where atmospheric pressure really is sort of not important. So when the pressure drops, it doesn't have to drop to atmospheric pressure. It can drop farther. It can go all the way to half atmospheric pressure. Atmospheric pressure is nothing special in that crack. And as a result, you can get less than atmospheric pressure between the two plates, in which case the atmospheric pressure pushing them together is stronger than the pressure inside pushing them apart, and they stick. So, okay, that's probably enough air to get them to stick. Right now they're pushing apart. It's close. I got to go more pressure. There they go. So it's wildly counterintuitive because the air is blowing down on that bottom plate and yet it's being stuck up. Yep. You okay with why that's happening? If I turn the air off, gone. So that's one. Another one is this funnel. This is sort of this very similar experiment, but it's just geometry changes a little bit. If I blow air through the funnel, sorry, the noise is irritating to everybody. Blow air through the funnel, of course, it shoots right out there. But if I stick a ping pong ball in there, the air then has to go through the narrow gap between the funnel and the ping pong ball. It necks down, it has to speed up as pressure drops. And it can keep it's sucked in there. Okay? Third one, there are a whole variety of these kind of gadgets. And the third one, this is a little bit more sophisticated. In this case, I'm going to take air and I'm going to blow it across a glass dome. And as it goes across that glass dome, it has to bend. Its path will bend. The total motivation, why does it follow that dome, is a little obscure. But let me draw it for you. Okay. Bye-bye, Pitot Tube. So here's the glass, there's the dome, and we're going to blow air across it. So there's the air coming in, and it's going to go over and around like that. Like that. The air is. Well, it's turning. It's a bend. The air is going to undergo a bend. And the bend is in this direction, towards the center, which is in the middle of the dome. So the air is bending toward the dome. Something's pushing it there. Well, the something pushing it is, there's atmospheric pressure out there. So that's the pusher. In order for the atmospheric pressure to win, to be stronger than the pressure near the dome, the pressure near the dome, oddly enough, has to be less than atmospheric pressure to allow the atmospheric pressure to push the stream toward the dome. You okay with that idea? Well, that dome has a hole in it. It's actually at the top of a tube. And the tube goes into water. And as the pressure here goes below atmospheric, so this basically addresses Reed's question. How do you know the pressure is high? How do you know it's low? Get access to it. Put a tube in there. So we're going to put a tube in that. It's essentially, we're putting a tube right there. Color's terrible. laser pointers, you get what you pay for. I didn't pay for much. So that region, we're going to put a tube in there. It's going to be low pressure. So here's the tube with the dome top. There's the water at the bottom. And this is how paint sprayers work. Or the old-fashioned perfume bottles. Or this things, opera singers, la 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 la, this is it. As the water goes around as the air goes around the dome, the pressure drops so low it sucks water out of the tube, entrains it in the stream of air, and blows a mist. Anybody have a cold, need a vaporizer? Here it is. Okay? Jokes aside, that really is how paint sprayers work. Airbrushes for sure. So any of you used airbrushes? There's a pot of paint. What makes the paint go up and into the spray? This. All right. With that, then, I think I'm done with this early look at the effects of water or airflow around curves, the bending of the flow. It involves pressure differences. So keep that in mind. We'll hit it again when we talk about airflow around balls, which is coming up momentarily. One more thing to talk about in the world of complexities of fluid flow. What if you don't have steady state flow? What if you start doing weird things like turning on and off the flow of water? Well, if you turn on the flow of water in a pipe, the water starts slowly and then builds its speed up to a certain level. Ultimately, it's going to be limited by viscosity. But you get the water moving, and it takes a little bit of time because you're exerting a force on it, and it doesn't pick up speed instantly. So it accumulates momentum. So water flowing in a pipe has momentum, like anything else. It's got mass, it's got velocity. Hey, it's carrying momentum with it. If you now go to the other end, so you turned it on slow, you turned it on and gradually started going and cruising along. You go to the other end and you stop it. You have another faucet or something, you just stop it dead. It's going to have to come to a stop, and that means you have to push it backwards. And the faster you stop the water, the harder you have to push. And how do you push on it? You push on it with a pressure difference. So it's going to have higher pressure at where it's headed, and it's going to have lower pressure behind it. So it's going to be pushed backward by that pressure difference. And if you want to stop that water that's moving packed full of momentum, if you want to stop it fast, you're going to have to push really hard on it by way of a giant pressure imbalance. So the pressure in front of the fluid, where it sort of hits the valve or faucet you just closed, that pressure surges upwards. It's now huge, and it can do stuff, often for better or worse. So I can show you that effect. It's known generically as water hammer. When you get the water moving, and it basically you stop it suddenly with whatever means you want, it stops suddenly by way of a giant pressure imbalance between the front surface and back surface, and it can damage things at the front surface as the pressure goes up. So this is a gadget that illustrates that. It's water in a tube with a complicated top on it and a reduced air inside. It's not got full atmosphere in here. But what I'm going to do is I am going to accelerate the tube downward fast with my hand. The water, because I don't touch it, the water, I won't push on the water, so the water will not accelerate initially. It will be left behind, which is to say it will sit here as the tube goes down, so the water will go up toward the top of the container. Is that okay? As it does so, it will compress the gas that's inside the tube and store it in this top as compressed gas. And when the glass tube stops accelerating downward, the compressed gas above the liquid will push it downward. The water will catch up with the tube. So the tube's initially going to leave the water behind, and then compressed gas up here will push the water to catch up with the tube. and the water will hit the bottom of the tube. There it is. You hear the snap? You ever heard a snap from water hitting glass? That, it's an unusual situation. I'm actually leaving the water behind, leaving a gap, and then having it catch up and hit. And if you do this too hard, the bottom of the tube breaks out. So once in a while, you're welcome to try this gadget here after class, but don't go too hard, because you can actually knock the bottom out. So we won't knock the bottom out of this tube. We will knock the bottom out of this tube. All right? So this is something to do this weekend with all the bottles that look like this. You do want to have the top to go back on, because you actually want to seal it to trap the air. So it's a little iffy. This is a root beer, okay? So I'll do the first one. You guys can do the rest. So I am going to push this down fast. It will leave the water behind. It's water now. I drank the root beer. I push it down. The water will be left behind and will go up into the neck of the bottle. When I stop accelerating the bottle, the water will catch up and it will knock the bottom out of the bottle. Like that. Who wants to try the next bottle? All right, Jane. And actually, you can do this whether you hit it with a mallet down or whether you take the bottle and hit the undersurface of a counter. Same effect. So I was in a grocery store when a woman took her bottles out of the basket and clipped the counter with them, and the bottom blew out. Okay, so you want to hold it tight, because you don't want to knock it out of your hand, and you smack the top. Do it over. Give it a good wrap on top. Yeah. Yay! One more person. All right, Alex. You're come on up. We got to finish the bottles off. Okay, Alex, you got it. It is possible to do this without a cap on there, with your bare hand. I've seen people do it. I've tried it myself, and I had donuts on my hand. You have to go ahead. Hey. You want, hold the body of the bottle. There you go. There you go. All right, thank you guys. Woohoo! Okay, so you're okay with why that happens? It's not a magic trick. It's you're actually getting the water to hit the bottom by leaving it behind, pushing it down with essentially compressed air, and having it hit the bottom and hammer it. And so this shows up not only in this sort of context, but anytime you drop something that contains a liquid, a can, for example, you drop a can of applesauce on the floor, when it hits, the container stops, the applesauce doesn't. The way to stop the applesauce is a huge pressure imbalance between high pressure at the bottom, low pressure at the top, and that high pressure at the bottom can be high enough to blow the sides out of the can, and often does. All right? That does it for the story of garden watering. And now we can go into the story of balls in air. And with balls in air, it can be any kind of ball, including things that you wouldn't normally think of as balls, like a car or an airplane. And so the issue that I want to pursue now is we see how fluids flow through various plumbing and around things and make bends and so on. What happens when a particular fluid, namely air, flows around a ball? And so just to pick a ball that's big enough that I can talk about it. When air flows around this ball, it has to do a number of bends. It has to bend away at first, it has to bend toward later on, bend away still later on. Those bends affect its pressure and its speed. And so let's watch what happens as air flows around this beach ball. And to make it all clear, how have I got my drawings arranged? They flow from left to right. Okay, so I'm going to have the air flow from left to right around the ball. Now, whether you hold the ball out in a wind or whether you take calm air and walk with the ball, the same thing happens. You get flow of the air around the ball. So just to make life simple for us and for the drawings and so on, we'll hold the ball steady and have the wind blow by. It's the same, it's exactly the same. You see the same thing in a thrown ball if you just walked along with it. You'd look over at it and it would look motionless to you as the air went by it. So as the air flows past this ball, and now it's big, but I'll live with it. It's flowing along and it encounters the front surface of the ball. That's the first thing it bumps into. It can't go through the ball. It has to bend away from the ball so as not to pierce into the ball. So the air up at the top-ish portion of the ball bends up to avoid going through. The air near the bottom-ish of the ball, I think bottom-ish is a technical term here. It bends down. The part near you bends toward you. So the air is spreading out. And we saw, I've talked last time, that when air does that, when it spreads out, it's as though it's going through a diffuser. It will slow down and its pressure will rise. So the air pressure at the front of the ball is above atmospheric pressure. You need that rise in air pressure to bend the air away. It's pushing the air away. Because the air out here is atmospheric pressure. The air there is higher than atmospheric pressure. That pushes. It pushes the air in all the directions. It pushes them away from the surface to prevent it from going through. So long and short of it is the pressure at the front of the ball, and I can show you this picture. Pick a color. Oh, come back here. The pressure at so this is what I've been talking about here. Ooh. This drives me crazy. Still not. This is the air. It's heading to the right. It encounters that surface. It bends away. The air going over bends up. The air going under bends down. The streamlines are getting wider apart here, indicating the air has slowed down. And the color shifted to violet, to the purple end of the spectrum. Violet end of the spectrum, which was my way of indicating high pressure. And that high pressure ultimately is what slows the ball down with air resistance, but we'll come to that later on. Okay, so the leading edge is, the leading surface is high pressure. You actually have experienced that high pressure in many contexts, one of which is when you're driving in a car and you stick your hand out the window, and ideally you're a passenger, not the driver. Okay, you stick your hand out, you feel, wow, it feels pushed backwards, right? You know, what's pushing on you? A lot of it has to do with that high pressure at front. And that high pressure in front is true at the front of your car, it's true at the front of an airplane, it's true at the front of you bicycling along. They all experience the same effect. So it's this universal thing. Okay? What about the air? What happens to the air next? So the air, I'll follow the air that was a little above center and bent around the top. That air first bends away from the ball, so as not to go through it. But if it kept on going straight, it would leave the ball behind. It doesn't do that. It wraps itself around the ball for complicated reasons, but it wraps itself around the ball, and as it goes over the top of the ball now, it's going over our dome. It's bending toward the surface now. And how can that happen? It must be pushed by pressure imbalance again. This is atmospheric pressure here, so the pressure at the surface must be less than atmospheric pressure, and it is. So the air bending toward the top and bottom and sides of the ball is below atmospheric pressure. So there it is in my drawing. Now I'm blue again. Too many opportunities. Okay, that air as it bends there, it's essentially going around a carousel. That's the center of the carousel. It's bending toward it. It's being pushed inward by atmospheric pressure. So the air there must be less than atmospheric pressure. And if you went in there with a gadget and measured it, sure enough, it's actually low pressure there. I essentially did that with my paint sprayer. This is just like the paint sprayer. We drill a hole in there and let it, and give it exposure to a bucket of water inside, it'll suck the water right out. Okay. Last thing, the air then continues on and has to leave the ball behind. And for that to happen, the air was bending toward the ball here. It has to bend away from the ball to leave. So something must push it away. There has to be high pressure behind the ball. which is not intuitive, that there be high pressure behind the ball. That sounds weird, okay? It happens because the air sort of bunches up there and blows itself away from the ball. So there will be, in principle, there is low pressure behind the ball. Is that okay so far? High pressure behind the ball. Problem. Air has a very low viscosity. It's almost no viscosity, which means that the ordering effects of viscosity are wimpy. If the air is moving too fast, inertia wins and you get turbulence. And the answer, so the air can't move too fast, otherwise you won't get that beautiful laminar flow at the back of the ball. And how fast is too fast? How fast is about as fast as your fingernails grow? In other words, the air going around the back of the ball almost always becomes turbulent. The only way you will get it not to be turbulent is to be in a weird situation where viscosity, where inertia, viscosity can still keep the flow orderly. It's tough. And there is a context in which it can do that. If the ball is really tiny, the ball is super, super little, viscosity only has to work over a very short distance, and even wimpy viscosities can keep the flow orderly. So how small does the ball have to be? Dust particles. So if I take dust particles, for example, these guys, you know, they're hovering in the air, kind of here, they're blowing out the door with the breeze. What is holding them up? Because after all, they're chalk, and chalk is not buoyant in air. Smash. Chalk should fall. That's chalk, that's chalk. That stuff didn't fall very well. The reason it didn't is because it started, let's imagine the air is totally motionless, and we drop a chalk particle. It starts to move down. It's falling. It starts to move down faster and faster and faster. As it does, the air begins to flow around it, doing all the tricks I've just described, and it stays orderly all the way to the back, the air does, and the chalk particle goes faster and faster. And the arrangement, I very slightly painted myself into a corner, but I can solve it. Yeah, glass. Okay, it does all this flow around the falling disk. I had to rotate the projector 90 degrees. But you can envision the dust particle descending through the air going around it. It actually does follow this kind of pattern. Perfect laminar flow, everything's great. This applies to dust, smoke, ash, clouds, mist, cold germs, all that stuff. You know, why do they hover in the air? They are trying to fall. They're getting this flow around them. This flow by itself, as I've drawn it, exerts no net force on the particle. Why not? Because there's high pressure on the forward surface, high pressure on the backward surface. They cancel. There's low pressure on the top, there's low pressure on the bottom. They cancel. All the forces cancel. And that by itself would say that there's no air force on the particle at all. It turns out we've left one other thing out. Viscosity. Air's got a viscosity, and it stops the air at the particle surface. I should say, the air is motionless at the particle surface, and so the motionless air at the particle surface and the air around the particle rub against each other as the particle tries to descend through the air. And they experience viscous forces. And the viscous forces tend to drag the air with the particle and at the same time keep the particle from going down. And I'll do this more carefully next time. But the effect is what's known as viscous drag. It is a force it's a force of air resistance that gives the particle a push opposite its motion through the air. And for dust particles and flue germs and all that stuff, that viscous drag force, is strong enough to equal the weight of the particle, even when the particle is only moving millimeters per second. The result is chalk descends through air super slowly. It's having a terrible time against the air resistance of viscous drag. And I'll do proper justice to that on Friday.